So we are going to hopefully get Michaelis Menten kinetics to work, where we have, this is our enzyme, and there's 1 milliliter of this in every one of these test tubes. Actually, for reasons that I'm not gonna explain, there's 2 milliliters in each one of these test tubes, but it still works out okay. And what we're gonna do is vary the substrate. The substrate is hydrogen peroxide, remember? And so we're gonna put increasing amounts of hydrogen peroxide in and measure the time to the line, which is our substitute for reaction rate. So you've got your data sheet. We're gonna start with 1 milliliter. We have 1 milliliter of hydrogen peroxide in the back test tubes to pour into the front test tubes. And so this is gonna be trial 1. Oops. That is, whoops, 1.46 seconds. Trial 2. .71 seconds. Now you see, if I had been a smart person, I would have put time in seconds up here so I wouldn't have to keep writing it in the boxes. But if you're ever making tables up, that's always a good idea to label your columns so that the units are already on there. This is trial 3. That is 1.03 seconds. Okay, when you're looking to maybe not use something, I'm looking at this and thinking, I may not have zeroed my watch when I took that. So I would subtract 1.46 from that to get the actual number. I'm just playing the beeps back through my head, and I don't think I beeped it. See, I have to zero this to use it, and I don't think I did between there and there. So that's actually that time plus that time. See, I have not yet finished making my mistakes. Okay, now I've definitely got this zeroed out. These are 2 milliliter things of solution. Oh, trial 1. Whoa, that's fast. Up and out. That was 1.06 seconds. Trial 2. I need to get it so I can see the line. Got to zero it. That was quick. That was 0.61 seconds. Trial 3. I hope you're getting the idea. This is not the easiest thing in the world to time. Okay, where the heck's the line on this one? There's no line on this, okay. I need to draw a line. At some point, I drew, all of the labels and the lines on all these test tubes. Okay, so that was 2, and this is 4. That goes back there. This goes here. So this is trial 3. Let's zero this out. Ready? That was 0.69. So faster. Now we're going to 3 milliliters of substrate.
Do you have lines on those?
Yeah, I can see the lines on these. Whoops. I'll be darned. This one's labeled 3 milliliters. They may, oh yeah, this one's worn off a bit. I mean, it's Sharpie, but if you handle the test tubes enough, it does wear off. Tap them on the table to make sure they're lined up at the bottom. It helps that I've got a little remnant of a line still on there. And as you can tell by the timing, doesn't have to be a real precise flat line, because I'm barely being able to figure out when the bubbles get to it. Okay, so this is 3. Trial 1. That was super fast. That was 0.32 seconds. This is trial 2. Zero 0.39 seconds. Nice to be working with something that isn't at all toxic, so I don't need to worry about it bubbling over onto the tabletop. Trial 3. Nope. I think I screwed that up. I did. So that one is, my fingers didn't work right. So you're gonna be averaging those two numbers together. Hold on. I can set up another test tube for that. So this is 3, right? Okay. Oh, that's empty. 1, 2, 3. Now it seems crazy, but when you're working in the lab, it's not a bad idea to say this stuff out loud.
You need to put a line on the test tube too.
Well, no, there is a line on test tube. Okay, let's give this a try. Make sure this is at 0, it is. Boy, that really is fast. So it was 0.34 seconds. Now we're at 4 milliliters. Okay. Trial 1. Zero 0.59. Trial 2. 0.47. These are so fast that I'm not entirely sure how reliable they are. I mean, 0.35. They're not getting significantly faster. Well, that's something. And this is 5 milliliters. I'm going to move them out into the middle so I can separate them and see them better. Okay, trial 1.
I can't see.
Oh,
You have to be careful where your hand is.
Zero 0.36. So we are either measuring the reaction time or how quickly I can move my fingers as this thing comes up and hits the line. That may be the second, because that was 0.36 also. And our last trial. Oh. .28. So these are all seconds. Don't want naked numbers. So, again, you do your averages and look for the pattern that you should have been expecting. The last thing to do are the questions. I'm just gonna go through them pretty quickly. If everyone produces different solutions, because everybody is mixing their water in their liver and grinding it differently, they're all gonna be different, then why are these tests reliable? Is that you have to figure out what it is you're actually looking at in terms of your results, that different people in the room with different starting catalase preparations are still getting comparable results. Point there is, what does comparable mean in this case? I put this lab together looking at a bunch of versions that other people have used, and in some other versions, instead of measuring to a point on the test tube, they use really tall test tubes and much weaker solutions and measure how high the bubbles go. Now, question 2 is, do you think that's a proper measurement? And if you do, why? And if you don't, why? In the test that we just ran, every test tube has the same amount of catalase to start. Why is that important? That one should be fairly easy. Now, number 4, catalase has 4 what are called hemes. These are prosthetic groups that contain iron. Give a way that might enhance its activity. If you think about it, you know about something else that has 4 hemes in it. And question 5, one important feature of activity is that the oxygen comes out, it comes out as O2. I mentioned that when we first went into it. Why is this better than oxygen atoms coming out as O1, as single oxygen atoms? That's something you should know from early in the semester. Okay, that is it for the lab.